Welcome. Good afternoon. My name is Dennis Irwin. I'm Dean of the Rusk College of Engineering and Technology here at Ohio University. When I introduced our fall semester soccer lecturer, 2013 Rusk Prize recipient, Dr. Rangaswamy Srinivasan, and a former colleague of today's speaker, I shared with you that a perk of my job is to participate in the Rusk Prize selection process and awarding process. I'm honored to present to you another soccer lecture made possible by our good friends Fritz and Dolores Russ, for whom our college is named, and who created the Rusk Prize. You may know that the Rusk Prize is the world's top prize in bioengineering. It recognizes an achievement, and I quote from the selection criteria, in widespread use that improves the human condition. The recipient of the Rusk Prize receives a $500,000 prize award, a commemorative medallion, and a hand-lettered certificate. Now, the perk isn't me standing up here at the podium, obviously. It's having met today's speaker and his colleagues, Dr. James J. Wynne, one of the 2013 recipients of the Rusk Prize, and others like him who epitomize what we in our college call create for good. Dr. Wynne, Dr. Srinivasan, and Samuel Blum discovered the technology behind LASIK and PRK surgeries while serving together at the IBM T.J. Watson Research Center in New York. They were honored a year ago during Engineers Week in Washington, D.C. with the Rusk Prize. And the citation reads, for the development of laser ablative photodecomposition enabling LASIK and PRK eye surgery. Their work has improved life for more than 25 million people, correcting vision problems such as myopia, hyperopia, short-sightedness or long-sightedness, and astigmatism for military personnel, emergency responders, and many of you in the audience today. So I'd like to see a show of hands. How many of you have actually benefited from LASIK or PRK surgery? Okay. Now what that means, since there are three, is that this is a young audience. Thank you. Dr. Wynne, currently the Program Manager for Local Education Outreach at IBM's Thomas J. Watson Research Center in New York, studied applied physics at Harvard, earning his PhD there in 1969. He spent a year and a half at IBM's lab in Zurich before making his permanent professional home at the Watson facility, where he currently leads communication and programming between or among local educators, students, and IBM's employees. Dr. Wynne was managing the Laser Physics and Chemistry Group in 1981 when he and his colleagues made their discovery with the Excimer laser. He's a fellow of many scientific societies and is a member of the National Academy of Engineering. President Obama awarded him the National Medal of Technology last year for his contributions to laser eye surgery. Before I welcome Dr. Wynne to the platform, I'd like to invite you all to a reception just outside the theater immediately following the talk. But without further ado, please help me welcome 2013 Rusk Prize recipient and creator of good, Dr. James J. Wynne.
Thank you.
James, welcome.
Thank you. Thank you for that introduction. I'd like to meet that guy. Some of you may have heard the lecture that my colleague Rangaswamy Srinivasan, who I call Sri, oops, got this one right, not double sound, stereo, gave in October. He concentrated a lot in his talk on how laser eye surgery works. I will not spend as much time on that. I will talk about what preceded laser eye surgery and what I hope to do after laser eye surgery, with a brief discussion of laser eye surgery. So excimer laser surgery, which we discovered along with Sam Blum, laid the foundation for laser refractive surgery, but there's more that can be done with it, and I'm working on that right now. I'll tell you about it. So here are all these fancy tools made possible by electronics. Isn't it wonderful? So that's where I work. I've been there since January '71. Eero Saarinen, famous architect who designed the St. Louis Arch for 150th anniversary of the Lewis and Clark exhibition, came to the grown-up world by designing St. Louis Arch, but he also built this nice building for me. And IBM research is not just in New York. We have 12 locations worldwide. We recently opened one in Africa, in Nairobi. I worked in the Zurich lab first after leaving Harvard, and then I've been back at the Watson lab. So I've been with IBM almost 44 years, and I'm really lucky. It's a wonderful place, and I'm surrounded with incredibly brilliant colleagues, and this cross-fertilization between the physicists and the mathematicians and the chemists and the computer scientists. We try to invent the future. That's what my job definition is, invent the future. And these are the type of things that go on in these different locations. The three places, the world has changed since I grew up, and at least in IBM, we've moved away from hardware. We used to make the entire computer from soup to nuts. Now we only make chips, but we can aggregate them together into computers, and we do all the software and applications. But we don't sell to consumers, we sell to companies, and we still make ultra high quality, incredibly fast microprocessors, but we don't make displays, we don't make PCs, we don't make disk drives. We invented all those things, but we don't make them anymore. So we still need some physicists because we're trying to make the next level of chips, and quantum computers and things like that. But then there are people like me who can sort of go off and dream and go after my dreams, like the next era of laser surgery. So the places where hardware is being done is Zurich, which invented the scanning tunneling microscope and later discovered high temperature superconductivity. The people who did that are people I worked with back in 1969 and 70, amazing people. And in Almaden, where he's now retired, Don Eigler used the low temperature scanning tunneling microscope and wrote IBM and atoms. That was a very amazing thing. The rest of the places are all doing software and services stuff. IBM had its 100th anniversary in 2011, and they picked 100 special things that happened over the history, the 100 icons of progress, and I'm happy to say that one of those 100 icons of progress was our work, which led to laser refractive surgery. So how did this come about? Well, the very first laser was the Ruby laser, May 16, 1960. And can anybody guess where it occurred? Where did the first laser work? Ted Maiman was the guy who created the first laser. What city in the United States was where the... No? West Coast. Nobody? Somewhere near Los Angeles? No. Malibu. Well, the surface came in of the Hughes Research had just opened a lab up on the hill above Malibu, and that's where Ted Maiman moved from the old Hughes Research near the Los Angeles airport. Got his laser to work May 16, 1960 in Malibu. Wonderful things happen in wonderful places. And already by late 1961, ophthalmologist at Columbia University was using a laser to treat a retinal tumor. So laser eye surgery on the retina started within a year after the laser was invented. Now, prior to our discovery, all laser surgery produced some damage, but that damage was therapeutic, such as producing a spot weld to repair a detached retina, or if you had a bleeding ulcer, I've got it up there, instead of sticking a balloon in your stomach or cutting you open, you would send a laser beam down and aim it at the bleeding ulcer and stop the bleeding. Always left some cauterization, some collateral damage. It was therapeutic. But the notion of removing tissue and having it heal without any scar tissue, that was not possible with all the other lasers. So it turns out that Sri had joined my group. I was manager of laser physics, and then I brought chemists in because we had some reorganization. And the photochemist, Dr. Srinivasan Sri, came into my group. And I also set out to hire some other people to do laser chemistry because we were a bunch of physicists. What do we know about chemistry? And then the Excimer laser, which had been invented in 1970 in Russia, in Soviet Union, became commercially available. And I bought one for my group on what I call a spec. We wanted to have a really good tool, short pulse, ultraviolet, high power laser. I didn't know what we would do with it, but it was going to give us capability to explore scientific frontiers that we could not do without it. That's our job, discover new stuff. And I encouraged Sri to think about using it, because he was using a mercury lamp to do his photochemistry, emitting far ultraviolet light at 185 nanometers, but it was a mercury lamp. Maybe a 193 nanometer short pulse high power laser could do something different. And with his assistant, Veronica, he discovered something that other people were probably doing but didn't recognize it. He could make incredibly clean holes in plastic with that laser. Each pulse of light from the laser took off a well-defined amount of plastic and left an incredibly clean hole. He probably talked about that when he was here, and it's in the video that was made. I'll show you another video later. Then he and I started talking about, if this worked so well on plastic, certain type of plastics, maybe it would work on human and animal tissue. The key idea there was that some of the plastics he was irradiating, some of the polymers, were things like polyimide that had a peptide bond. The chemical bond which was absorbing the light was a peptide bond, and that same bond exists in your skin and in human tissue. So if it's being strongly absorbed by the polymer, it might be strongly absorbed by your skin and make a beautiful, clean incision. And I would also say that the insight that I had, whether it was going to be correct or not, you all know, every one of you I'm sure knows, that if you cut your finger with a razor blade or get a paper cut, a thin, clean cut, it hurts and it bleeds, but if you keep it clean, it heals without scar tissue, right? Does everybody know that? Does anybody not know that? Well, I knew it from when I used to cut myself as a child. So if the laser could make a clean incision without producing any damaged tissue on the side, and the wound or incision was very clean, it would heal without scarring. Maybe. So Sri and I talked about how we're going to check this out. Meanwhile, we brought Sam Blum into our group because he's a material scientist. We wanted different expertise. And Sri and I talked about trying butterfly wings, goldfish tail. But he took the big step forward, and the day after Thanksgiving in 1981, November 27, 1981, he brought his Thanksgiving leftovers into the lab, had a turkey bone with some meat and some protein and some cartilage, and he irradiated that cartilage and made a clean groove in the cartilage. Now, since the cartilage was smooth and white and sort of flat, you could see what you had done. Because we were talking about hamburger meat from the cafeteria and all sorts of other things besides the butterfly wings and the goldfish tail. But the cartilage turned out to be the perfect sample to test this out. And having already done this on plastic, he kind of recognized what was happening. Now, he and Sam then did this a little more carefully and quantitatively, and then they gave me the sample at some date that I don't remember, but roughly 2 weeks later. And I used the laser that I was using for my own science, which was a green laser. Instead of an ultraviolet laser, it was green color, more powerful than this. It was something called a frequency doubled Q-switch neodymium YAG laser. But just remember, it emitted short pulses of green light. And the difference when I irradiated that turkey cartilage with this green laser, I burned and charred it, totally different morphology than when you irradiated it with the ultraviolet, far ultraviolet Excimer laser. That was the moment of aha for me, the discovery. We had a new form of laser surgery. And I will show you a movie in a minute where I use words like that. So we wrote up an invention disclosure, and Sri and I signed off on it on December 31st, 1981. And Sam, who was on Christmas vacation, came back and he signed it on January 4th. And then we submitted it to the IBM patent people. We got a patent, and this made us the first. We were the first people to recognize this. Other people were testing this laser out to see eye damage. Every new laser, you wanted to know if it was dangerous. And they were radiating live rabbits and looking for eye damage, and were undoubtedly photo etching it this way, but didn't recognize it because they didn't have this trained mind that we did and expertise, and good luck. That combination allowed us to recognize something that was going on, and anybody shining this laser on rabbit eyes would have been doing the same thing if the fluence were high enough, but they simply didn't recognize it. They were looking to see how much damage would be produced at a different fluence to know what the safe level was. So here's this video clip, and when I show this, if I can get the light turned down a little bit, that would be nice. This light shining in my face. So the first pieces of this are going to be just words. This is an excerpt from a video made in 2002 for a television program called Serendipity that was shown on the Discovery Health Channel in June of 2002. And it combines two stories to make it nice for the television audience, but the story about the girl with the port wine scar has nothing to do with us. The audio? It was playing before. Hello, audio? It's plugged in. Okay, I will halt this and talk a little bit here. So this was, Sri and I and Sam Blum were inducted into the National Inventors Hall of Fame in 2002, and that announcement was done in May. The production of this video was totally serendipitous, just like the movie is called Serendipity, because IBM PR people got in contact with whoever produced this video, and they said we had the story about the turkey. Everybody loves the story about the turkey. So people came to the lab and videoed me, and we put some other stuff together, and they put it on television back in June of 2002. And should I, anybody there? I could turn this on, unplug this, and just hold my microphone against it. You know, we have to innovate.
Birthmark that's impossible to hide.
When kids started teasing me, that's when I realized that something about me was
You hear it?
different.
Is it? Oh,
A
so yeah,
solution
nice.
called laser therapy.
You have this one wavelength of light, you collimate it, and you make it coherent. So the wavelengths of light go together, they all come out, which makes it very powerful. I mean, it's amazing.
All from the serendipitous inspiration of a Thanksgiving turkey.
And what could be more serendipitous than to bring in a piece of turkey from the Thanksgiving dinner and irradiate it and then observe that it could be a new form of surgery? That's unprecedented. Nothing like that has ever happened before. This is what I used to watch back in young days when I was young, in the 50s. Flash Gordon, Dr. Zarkov.
Lasers first entered the popular imagination through science fiction.
So when I was a kid, they had Flash Gordon on television. These movies were made in the 30s and then shown on television before we had programming. Zarkov, physicist. This was ultimately the way I imagined myself. And Zarkov was always coming up with scientific solutions to fend off the bad guy who was Ming the Merciless. Ming was very bad.
Jim Wynne was captivated by lasers. For him, they evoked a new era where technology takes care of all problems.
This is a Martian. The
Bad
Flash
guys
is
from outer
disguised as a
space.
Martian. And suddenly this beam of light appeared going across a chasm, and it made a noise like zzz, and you saw a beam of light. And the physicist said,
What is this? Where are you taking me?
These Earthmen must be a stupid lot. He's evidently never seen a light bridge before.
and I thought, gee, what's light? You can't walk on a beam of light. And then they walked across the beam of light. Hollywood.
A laser is a very special light source. A high-intensity beam, much brighter than regular light.
This is the commercial Excimer laser that we had several of in our lab, made by Lam de Physique in Germany. That's the